All right. How's everybody doing? All two of you. How's the homework going and everything else?
Had bad time management since Tuesday.
You did what?
I've had bad time management since Tuesday. And I kind of misplaced how long it would take to do.
For this class?
Like for this assignment.
Oh, this assignment?
I got most of it. It's just like it took me.
Would you like some more time to complete it? Because I'd rather you understand it thoroughly than turn it in and turn in some,
I was gonna turn it in on Tuesday.
Okay.
That's already.
Of course, yep, that's fine. For the students that want extra time to turn in better quality work, I always say yes. But you have to be careful not to fall behind. Those deadlines are mostly there so people don't fall behind. If there is no deadline, then people, even myself included, might put things off and off and off and off. And so then you put it off for so long that it's like now you put yourself in a hole you can't get out of, in terms of time. Yeah, in terms of the number of assignments and the time.
You do your own grading.
Yeah, so like the deadlines are mostly there for your benefit. Okay. Section that we did last time. Oh, yeah, we did the sum parts. No, we did the 5.2 sum and difference identities. Okay, so we're on 5.3. Double angle and half angle identities. All right. Okay, so do you guys remember that we found, what did we find? We found that the cosine of some alpha minus a beta is equal to cosine alpha cosine beta plus sine alpha sine beta. Is that right? All right. Okay, and then we were able to say, okay, set beta equal to a minus beta in this equation. So then we get cosine of alpha minus a minus beta. Just notice this is the same thing as cosine of alpha plus beta, is it not? So then we realize that that's equal to cosine of alpha cosine of negative beta plus sine alpha sine of a negative beta. And then we use the even property of cosine to make that beta, the negative and the beta, go away. And we use the odd property of sines to have that minus sign appear on the front. So cosine of alpha plus beta is this. Now, what if we were to say set beta equal to alpha? So then this equation would then become cosine of alpha plus alpha, right? Which is cosine of 2 alpha. Right? Prepare yourself to discover a new identity. the double angle formula. Cosine of 2 alpha is what happens when we replace every beta in this equation with the alpha. So then this becomes cosine alpha minus sine alpha. Is it not? Yeah, it is. So actually, cosine of 2 alpha reduces to cosine squared alpha minus sine squared alpha. Following me so far? We started off with this thing that we derived together using this is the angle beta, then this is the angle alpha, then this distance is this, and bring it down, and this distance is that, so the distance is equal to each other, square algebra, and solve for cosine alpha minus beta. We got this. Then we were able to discover the new formula, cosine of alpha plus beta. So you guys, this is how mathematicians do it. But you guys could just use this as given. And you could just use this as given. I'm just showing you that you don't have to memorize. You don't have to memorize, really. That's what I'm showing you. That's it. That equation is cosine of alpha plus beta. All right, so we've discovered a new identity. This is called the double angle formula, because there's a double angle in here. Right? Now let's continue to discover more identities. I mean, this is how the mathematicians of antiquity did this. They, from first principles, from first ideas, invented new ideas, which to us is the most beautiful thing ever. It's like, who here has like grown plants before? Who here has like put something in soil and watched it grow? I mean, they should have made everybody do that as little kids, in kindergarten or whatever. Grow your own plant. Mathematics is like that. When you plant a seed, and if you cater to that seed, it grows and grows and grows and grows, and just gives you more and more and more. Tiny little bit gives you so much. I have tomatoes. Oh, okay. I was like, why are you telling me you have tomatoes? Oh, you mean you've potted plants. Okay. I was kind of confused with that one, but no, I'm not. All right. What about for sine of 2 alpha? Can we come up with the equation for sine of 2 alpha? What does this equal? I don't know. But what do we know? That the sine of alpha minus beta, correct me if I'm wrong here, this is sine alpha cosine beta plus sine beta cosine alpha. Sine alpha cosine beta minus, when it's alpha minus beta, minus sine alpha cosine beta minus sine beta cosine alpha. Okay. So I can discover what sine of alpha plus beta is, right? Because this is the same thing as right? So then that's the same thing as sine alpha cosine of a negative beta minus sine negative beta cosine of alpha. What does this reduce to? This is an even function, so that minus goes away inside. So I get sine alpha cosine beta. Over here, this is an odd function. The minus comes out in front, which cancels with that to make it plus. Plus sine beta cosine alpha. And I don't need these parentheses, but they're technically always there. Parentheses are technically always there. Haha, got a new equation. We knew this identity right here, right? But I know that I can use this to extract a new equation for this. In this equation, set beta equal to alpha. Let beta over here equal alpha. Once you do that, this becomes sine of alpha cosine of alpha plus sine of alpha cosine of alpha. Notice that that's the same thing added to itself. So it's 2 sine alpha cosine alpha is equal to what the sine of a double alpha is. You can just take what is in here in this box is given, but that's how you find it. That's how you derive it. So we have now discovered what cosine of 2 alpha is and what sine of 2 alpha is. Right? Let us continue. Let us forge ahead and excavate more knowledge, more truth. What else can we do? Oh, wait. I flipped 2 of, okay. Now, notice that there's even more possible expressions for the cosine of 2 alpha, right? Let me clear up some real estate here. What do I mean by that? Well, if the cosine of 2 alpha is equal to this, and sine squared alpha plus cosine squared alpha is equal to what? What is that equal to, class? One. Notice that I can solve for cosine of alpha, cosine squared alpha here. And plug that in here. Notice that this implies another equivalent formulation for the cosine of 2 alpha is, if I replace this cosine squared of alpha with this 1 minus sine squared alpha. That goes here, and then I got to put a minus And that always equals our cosine of 2 alpha. Oh, but notice that that minus itself, this implies that this equals 1 minus 2. Okay, so which one is right? Is this right or this right? Which one of them is really cosine of 2 alpha?
Both of them?
They're both right. Excellent, Travis. When you're Travis, you're Joshua. Can you believe I just like dyslexically change your names? That's why sometimes I stare at things for a long time because my brain is flipping them and I have to reflip them back and then I flip them again and I got to reflip it back. It's a fun game, but it takes a long time to do things that most people are like, I take like 30 minutes to do it. Okay. Notice that, in this formulation, we had a cosine squared alpha, and we solved for it and plugged it in, and we got a new identity. But notice we also have a sine squared alpha. Can we solve for a sine squared alpha and extract a third equivalent expression for cosine of 2 alpha? Yes, we can, can't we? Let's do it. So in this expression, we had plugged in 1 minus sine squared alpha for cosine squared alpha. But notice that using the Pythagorean identity, and instead now solving for sine squared, we get sine squared alpha is the same thing as 1 minus the cosine squared of alpha. So I can actually replace this thing with all of that. And don't forget to put some parentheses on it. Cosine squared alpha minus, this goes here. Right, so that becomes 1 minus cosine squared alpha. So notice that once the negative distributes and this becomes a minus 1 and that becomes a plus cosine squared alpha. So it's cosine squared alpha plus cosine squared alpha minus 1. So that's 2 cosine squared alpha minus 1. And this is our third equivalent expression for the cosine of 2 alpha. You guys could just use this. For your exam, I'll let you write these identities on a sheet of paper or something, or I'll put them on the board. You could probably put them on a note card or something. But this is where they come from. This is the derivation. I don't want you guys to spend your time memorizing. Poor Joshua does enough of that. He's a pre-med. I also was a pre-med, so I know for sure what you're going through. Just keep sipping that coffee, man. Also, don't forget to drink the equivalent, if not double the amount of water as to the coffee. The coffee is a diuretic, and for however much liquid coffee you drink, that's how much the diuretic will expel out of you. So you got to double it. Double that cup filled with water to be full, replenished in terms of being hydrated. This is coming from someone who OD'd on caffeine and had to go to the hospital for dehydration.
Oh.
I learned my lesson, so I drink a gallon a day. I learned my lesson. What a gallon a day is really kind of on the extreme side, but it does make you feel good. So we found we found 3 equivalent formulations for the cosine of 2 alpha. We found 1 formulation, or identity, if you will, of the sine of 2 alpha. What about tangent? Tangent's sitting here all lonely. It's like, what about me? So Joshua, I will relieve you of your memorization load. You will get these formulas. I'll either put them on the board or you guys can write them on a note card. I will not expect you to memorize these things. I just want you to be able to know how to use them. And do I want you to know how to derive them? Yes. Will I expect that of you? No, but maybe for a bonus question, I could, because it's bonus. You know, to get those points, you have to go above and beyond what's expected normally for a trig class. You know, standard things in trig are okay, you know, use this in a situation, you know, use the formula. Higher above expectation is, you know, using one identity derive the next. Yeah, so I will give more reward to those who go above and beyond and try and learn this stuff on a more fundamental level, but it's not fully required. I could not make that required. That is not, well, it just wouldn't be correct. It just wouldn't be right of me to do that. But it's fair game to give additional points to those who do want to go to that level, which then inclines you to do it, even though you don't have to. It's my way of trying to like influence you to become either, you know, into a mathematician or more mathematically inclined. I want all of you guys to actually convert to becoming math majors. And you could stay a computer science major. A lot of people double major in computer science and math, and you'd be really well off if you did that. You get hired like this. What about the tangent of 2 alpha? Well, that's the sine of 2 alpha, or the cosine of 2 alpha. So, we only have one choice for sine of 2 alpha. Which one of these do we pick? Well, which one of these do we pick? Well, they have that. The identity is 2 tangent alpha divided by 1 minus tangent squared alpha. So if we aspire to derive what they have, we might want to pick one of these tactfully, right? Because the sine of 2 alpha has a sine of theta and a cosine of theta in it. But in the denominator, this cosine of 2 alpha has a myriad of possibilities. But if we wanted to somehow turn into a tangent squared alpha, which is sine squared alpha over cosine squared alpha, we might want to set it up to where there's a sine squared alpha in the denominator divided by a cosine squared alpha, right? So we might want to pick this formulation. Or we might want to pick that formulation. Why I picked that one, I looked at this one and it was mouth-watering. But then I realized this is even more mouth-watering if I want to achieve this result. Why? Well, I could just factor out a cosine squared alpha from the denominator. So this becomes 1 minus. Does it not? So then delete these here. So then, bringing the calculation over here, this then equals, I can cancel out a cosine alpha here. So then, once those cancel, now this is 2 sine of alpha over cosine of alpha, which that gives me 2 tangent alpha. And then I have 1 minus sine squared alpha over cosine squared alpha. But that's just the tangent. 1 minus a tangent squared alpha. Oh, boom, boom. So out of the 3 possibilities, I picked the one that would get us to this identity that they require us. Could picking the other ones have still given us this result? Absolutely. It might have taken some more work, or you might have gotten it to achieve some different like variation of this. It might be really this, it just looks a lot different. So what you guys need to do is just know how to use this. Now I will say, verifying identities is part of the curriculum in this course. So what I'm showing you is something you're expected to know how to do to verify identities. All right. But these are special identities that you can just have on your note card or whatever. But why not take the chance to do both, right? Help you practice verifying identities on top of giving you the identities that will be given. Now that we've established these things, why don't we apply them? So if sine of alpha is equal to 5 over 8, whoa, it's like I'm writing with my left over here. 5 over 8, find the value of cosine of 2 theta. What is the cosine of 2 theta? Given that that is what our sine of alpha is. Well, it would have been helpful to have those things I had outlined here. But we had several expressions for cosine of 2 alpha. The one we want to go with is the one that has cosine of 2 alpha purely in terms of sine. Because the only thing we know is what sine is. So we want to pick the one that only has the sine equation in it. And that was 1 minus 2 sine squared alpha. Okay. But what the way we solve this problem is, we want to know what cosine of 2 alpha is. We're only given what sine of alpha is. We re-express cosine of 2 alpha in terms of sine of alpha, and then we just replace 5 over 8 here and square it. So whatever that ends up being, that is what the cosine of 2 alpha is. So that ends up becoming 1 minus 2 times the quantity 25 divided by 64. And that equals 1 minus 50 divided by 64. And then multiply top and bottom by 64 here. I get 64 minus 50 divided by 64. And that becomes 14 over 64. cosine of 2 alpha is equal to 14 over 64. Given that the sine of alpha is 5 over 8. Any questions?
Question, did you only multiply the 25 by 2?
Did I mess up a calculation? Did you say something?
No. Did you only multiply the 25 by 2 and not the 64 on the bottom?
Did I only multiply the 25 by 2? Yes, Anthony, because this 2 is really a 2 divided by 1.
Okay. That makes sense. Appreciate it.
No problem. But all right, let's move on to the next problem. Notice that that actually can get simplified to 7 over 32. Same thing. It can also be simplified to 7 over 32. Same thing though. Right? That's just simplifying it. So let's do another example of how we could apply these two concrete examples. Verify that cosine of 3 theta is equal to verify this identity, that it's equal to 4 cosine cubed theta minus 3 cosine theta. Four cosine cubed theta minus 3 theta. Minus 3 cosine theta.
Is that a 3 theta in the cosine to the left, or is that 30?
Oh yeah, it's a cosine of, let me say it all from the beginning. Cosine of 3 theta, show that it equals 4 cosine cubed theta minus 3 cosine of theta. So it's not 30. Yep, that's a good question. So let's prove this. So to prove this, we actually have to start with one equation, do algebra and substitutions on it in order to arrive to this other side. So let's pick this side and go here, or we can pick this side and go here. Want to know which one I'm going to pick? I'm going to pick the one that we're most equipped to do, given what we've just reviewed. And that's start with this side. And I usually say start with the more complicated side, right? But actually today, this gives us more to work with, because a 3 theta is the same thing as theta plus 2 theta. Is it not? And we can say that, call this an alpha, call this a beta. And so cosine of alpha plus beta becomes cosine of alpha, cosine of beta minus sine alpha, sine beta. You see what I did there? Does everybody see what I did there? If you don't, say so. Okay, so everybody sees what I did there. But we're supposed to get to this 4 cosine cubed theta minus 3 cosine of theta. After doing that, it doesn't really see, I don't really see, we don't really see how that's, you know, how that's even going to happen. Oh, one thing I do know, this has a formula for it that we've discovered today. So notice that then we could rewrite everything. This is cosine of theta, cosine of 2 theta, minus sine of theta times what is the sine of 2 theta equal to? You guys at home, can you see what's on the chalkboard? Is the red easy or hard to see?
A little difficult, like the cosine part.
I will not use red. I actually assumed that that was true. I actually know that that's true. If I know better, why am I doing that? So now what do we have? Well, this means I have cosine of alpha, cosine of 2, or not alpha, but theta, minus 2 sine theta, but now 2 sine squared theta, cosine theta. That's what we have here now. Okay, so now what? Because we still don't have this. I need some cosine cubes in here, and I don't. I need a normal 3 cosine over here, and I have a sine squared here. It seems like a disaster. Oh, guys, didn't we have a formula for this? We had 3 different formulas for this, didn't we? Yeah, which one should we pick? If we want this to somehow turn into a cosine cubed theta, we should probably pick the formulation for cosine of 2 theta that had a cosine squared in it, right? Because cosine times a cosine squared gives me a cosine cubed. And which one of those had the cosine in it? Oh, that was that cosine of 2 theta was the same thing as, let's look back in the past. It was the same thing as a 2 cosine of theta squared minus 1. So I can directly substitute that here. So bringing the calculation up here, because I'm running out of room, I get cosine of theta times this, the quantity, 2 cosine squared theta minus 1 minus 2 sine squared theta cosine of theta. Didn't manipulate that at all, just change this. So I'm going to have to delete some stuff here because I'm running out of room. So then bringing this calculation down here, I distribute the cosine theta. So I get 2 cosine cubed theta to this. And then to that just becomes a minus cosine of theta. Minus 2 sine squared theta. Cosine of theta. Now, we're starting to get close to this here, because we got a cosine cubed, and that's good, but there's no 4 here. We want a minus 3 cosine of theta here, but we got a sine squared, and I don't, you know, what's going on there, right? But notice right here, what could we do with these terms here? They have a common term in them, and what is that? Yes, yes, yes. We can factor out a cosine of theta. So then this becomes minus 1 minus 2 sine squared theta. When we factor out a cosine of theta,
And it became a 2 cosine squared theta because you factored it out.
it becomes a 2, what?
At the beginning, it's 2 cosine squared. Or is it?
That's a sine squared.
Okay.
The squared is on the sine.
No, I meant like at what you wrote at the bottom, like 2 cosine. Is that squared theta plus cosine theta?
Yeah, because I'm just rewriting this. Oh, that should be a cubed. Is that what you're saying?
Yeah, I was like,
Yes, 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 you're correct. That should say cubed. I dropped my cube. Thank you very much. So now, notice that what's in here, what can we do with that? That looks hauntingly like one of the identities we had. Does it not? Which one of the identities does that look like?
one minus 2 sine squared theta, or alpha, equals cosine 2.
Say it again. You said 1 minus 2.
2 sine squared alpha equals cosine 2 alpha.
2 sine squared alpha equals what?
Cosine 2 alpha.
This one?
Yeah.
But there had to be more to it than just this 2 sine squared alpha.
Yeah, I said 1 minus 2.
Aha, aha, aha. Now, that's a great idea because this kind of does look like that, but it's not exactly. There's a minus here instead of being a plus here. Secondly, even if this was directly that, that would take us to a cosine of 2 alpha, and that's not here in this final expression in which we desire to represent it as. That's a brilliant guess, though, but this is not what we want to do. Notice what we could do. Notice that this cosine cubed theta still is at a 2. It's not at a 4, meaning we still might need to add some more cosine cubed thetas to this to become a 4 cosine cubed theta, right? Notice we have the opportunity to introduce some cosine squared thetas here. and multiply it times the cosine of theta to turn it into a cosine cubed, then we can add it here. So why don't we somehow convert that sine squared theta to a cosine squared theta? How would we be able to do that? Which identity gives us the power to do that? Right? So right? So then I can plug this in here. So then I get this is equal to 2 cosine cubed theta plus cosine of theta times 1 minus times -1 minus 2 times what this is, sine squared theta. But that's really all 1 minus cosine squared theta, parentheses, close. Okay. Bringing this down, notice that this is 2 cosine cubed theta plus, let's deal with what's inside these parentheses here. Cosine of theta multiplied times this -1 is just -1, and this -2 distributes to these two terms. So this -2 times a -1 gives me a negative, this -2 times a +1 gives me a -2. Then that -2 distributed to this gives me a positive 2 cosine squared theta. And this is all being multiplied times the cosine of theta. You guys see that? Then this adds up to become a -3. So then this becomes a 2 cosine squared alpha. Or again, I dropped the cubed. Don't drop the cube. All right. Then notice that cosine of theta times a -3 gives me -3 cosine of theta. Oh, that's really good. That's in our final expression we want to find. But we're not done distributing. That cosine of theta needs to get distributed to this -3 and to this 2 cosine squared theta to give me a positive 3 cosine cubed theta. Oh. But what's going on here? Why did I just say 3? This needs to say 2. The coefficient out in front was 2. That doesn't change. The power changes. Okay? So then, when I combine 2 cosine cubed theta with another 2 cosine cubed theta, I get a 4 cosine cubed theta. And then this -3 cosine of theta comes along for the ride. And notice that that is the final value. That is the final expression that we wished to achieve. This stuff takes practice. You guys have to practice this stuff. It's going to take practice. But you guys are able to do it. Just keep practicing and you'll be able to do this. One of the beautiful parts of mathematics is that it does require a little bit of memorization, but most of it is deductive reasoning. And that doesn't require memorization. That requires the ability to think and to think critically about solving a problem. How can I use what I know to get to this point here? You know, we interchanged different strategies and we saw that, oh, that strategy, although it seemed promising, wouldn't work out. Let's try a different strategy. That's how you got to do these problems. You got to try something, If it doesn't work, okay, step back, try something else. If that doesn't work, okay, step back, try something else. Professional mathematicians do this all the time. And there are certain problems in mathematics in which mathematicians have been stumped on for hundreds of years, and they still don't know the answers to those problems. One of them being the Riemann hypothesis. It's very interesting. It has to do with the distribution of all the prime numbers. But anyways, that's just the nature of mathematics. We make highly educated guesses and see if it works. It's, seems like, oh, well, I'm just guessing. I'm just shooting in the dark. But the better you get at mathematics, the better you get at guessing, the more educated your guesses become. Okay. I want to give you guys a quiz because it's Thursday, but I'm not going to. It's up to me, I can give quizzes if I want. There's just already so many quizzes that I haven't graded and handed back to you yet. That pile, I don't want it to grow one more quiz.
Thank you.
Yeah, you're welcome. I just don't want it to grow one more quiz. Why don't we just continue lecturing? And because this section is probably going to be a pitfall for some. And even if it's not a pitfall, it's a pitfall for all. Some might get out of the pit and others might struggle to do that, but you guys can all get out of the pit. You just got to work. You got to put that elbow grease in. You got to keep trying. And sometimes life is really distracting. Things are around us and they distract us from, our assignments and what we have to do. But you guys always have to, number one, take care of yourself, take care of your health. That's the number one thing. But you also have to realize that, even if things are going on around you, at the end of the day, you're in college to invest in yourself, so that you can then go on to have a better career, a better resume, and hopefully a better life. And so the harder you try in your classes, the more prepared they should be making you for your career in the future. I can't say that for all classes, right? I can't say that for all classes. Not all classes will help you in computer programming that you're forced to take. Composition, writing essays. How's that going to help you debug your code? Maybe writing essays will help you write a formal report, a medical report. And I don't know about Travis. I don't know what he's wanting to major in. I hope it's math. Do math. You should do math. You should talk to Dr. Zoller and ask him about all the possible, because you don't know what kind of career you want. Math is the major to give you the most versatility in any kind of career you could want to get. Yeah. So this is one of those classes that will benefit you guys. It would totally benefit you guys. Even the pre-med, it would totally benefit you. Because what about you have a differential diagnosis that nobody can figure out? Patient comes in, they have all these symptoms. The symptoms don't add up to something very common. You have to diagnose the patient. Critical thinking and reasoning kicks in. It's not just a runny nose and a fever. It's some weird stuff. Intermittent tachycardia coupled with vertigo and this and that. And then you're like, oh, there's other symptoms and their blood work is strange. And you have to kind of figure out, what do they have? Like some type of tropical parasite that they got on their vacation trip or something. You have to figure that out, and that's going to be fun. But you use deductive reasoning. You pick a diagnosis, you see if the diagnosis fits. If it doesn't, then you go back to the drawing board, you think of another diagnosis. I don't know what kind of field of medicine you want to go into. That's kind of really early. But I wanted to be a diagnostician. yeah, I wanted to just focus on that stuff. Then I realized, chilling in the hospitals is not for me. Okay. And you guys may change your career pathways, and you might want to switch to mathematics, which would be really good. Or you might not. It's okay. The world will not end if you don't become a math major. My job is to try and convince you that it would be very fun and that it would be very useful if you did. Okay. Next, let's talk about the power reduction identities. What is a power reduction identity? Well, what it does is it wants to reduce the power of the trigonometric function. Right now, these are squared, but we want to bring that down. We want to bring that power down. So how do we do that? Well, remember our good old cosine of 2 alpha? This is a very useful identity because it had 3 different formulations. One of the formulations was that it equaled 1 minus sine squared alpha. Right? But notice that sine squared alpha, if we wanted to reduce its power, we could just solve for sine squared alpha in this. It used to be the cosine of 2 alpha identity, but now we can call it a sine squared alpha identity by solving for sine squared. So this becomes a cosine 2 alpha minus 1. And then if I want to know what sine squared alpha is, I multiply or divide both sides by -1, and I get that this is equal to 1 minus cosine of 2 alpha. There is actually a 2 here that I dropped. So let's not forget that there's a 2 here. And so at the end, it is 1 minus cosine of 2 alpha when we distribute the negative part, but there also needs to be that dividing by 2 part, right? We also got to divide it by 2. When I wrote this, I forgot to put the 2 on it. So in your notes, just know that there needs to be a 2 there. So this is a power reducing formula for sine squared alpha. I got the power 2, and now I can re-express this trigonometric function of power 2 as a trigonometric function of power 1. Power reducing. What about cosine of alpha? Well, this handy dandy cosine of 2 alpha also has an equivalent representation where it has a sine or a cosine squared alpha in it. And what was that? It was a 2 cosine squared alpha minus 1. Solving for cosine squared alpha, we can attain another power reducing formula. Right, so then when I divide both sides by 2, I get Isn't that cool? We're able to reduce its power. We were able to express it as a reduced power. Why is this important? Well, it just gives you more identities that you can work with. You have more identities. More identities means more tools in your pocket. You have more tools when you have more identities. So now, the more identities you have, the more tools you have. The more tools you have, the wider variety of accomplishments you can do. So what about tangent squared alpha? Tangent squared alpha is the same thing as sine squared alpha over cosine squared alpha. But when I use these guys, I get 1 minus cosine of 2 alpha over 2. That's for sine squared alpha. And I have 1 plus cosine of 2 alpha over 2 for cosine of 2 alpha. Notice that when I multiply by reciprocals, the 2's cancel. So I get 1 minus so that's what the power reducing formula for tangent squared alpha is. So let's apply this. Let's write a sine to the 4th in terms of trigonometric expressions of power 1. 8 sine to the 4th. So what we aspire to do is meaning let's reduce the power of 8 sine to the 4th x. Okay? 8 sine to the 4th power x. That's 8 times sine squared x times sine squared x, is it not? Or then we could just use a pair of power reducing formulas. Bringing the calculation over here, these two multiply to give me a 4, and I can factor out a 4, and I get 8 over 4, which is a 2. Then we FOIL the numerator, or distribute. I don't like FOIL. This becomes 1 minus cosine of 2x minus cosine of 2x plus cosine squared 2x. Close parentheses, distribute the 2. This becomes 2 minus 2 cosine of 2x. Oh, wait, no. No. We can combine these two because they're the same thing to be 2, negative 2 cosine of 2x. So then when that 2 distributes, I get a 2 minus a 4 cosine of 2x plus 2 cosine squared 2x. We've reduced the powers from 4 to 2 and 1, but I want this one to not, because I want all the powers to be in power 1. Now that cosine squared needs to get reduced, but I unfortunately deleted the identity that could have been used to find it. but you need not worry. I'll just write it up there. Cosine squared alpha is the same thing as is it plus? Yeah, plus. Okay. So, but that's for cosine squared alpha. This is cosine squared 2x. So when we have to use that appropriately. Okay. So alpha, set alpha equal to 2x. And plug that in here for the yellow. So notice that we're going to get 1 plus cosine of 2 times alpha, right? But notice 2 times alpha, if alpha is equal to 2x, then 2 times alpha is equal to 4x. So here was our identity. Cosine squared alpha is equal to 1 plus 2 cosine of 2 alpha divided by 2. We have this situation right here. So we notice that we're going to have to set 2x equal to this alpha. So if cosine squared alpha is equal to this, then cosine squared 2x is the same thing as cosine squared alpha. So it's the same thing as 1 plus cosine of 4x. Because remember, 2x was set to alpha. Because here. But we want to know what 2 alpha is. But if alpha is equal to 2x, what is 2 alpha multiplied both sides by 2? You get 4x. So if this has 2 alpha in it here, then this must have a 4x in it here. And now you're done when you cancel out these 2's. Because we've reduced the powers to trigonometric expressions. Power 1. These combine to give me a 3. 3 minus 4 cosine of 2x plus cosine of 4x. So a sine to the 4th x is equal to 3 minus 4 cosine of 2x plus cosine of 4x. Isn't that crazy? That's wild. Who would have thought? I mean, who could have guessed that? It'd be so hard to guess that this is true. But with the identities and the mathematics, you're able to see that, oh, yes, indeed, it is true. But this is not obvious. That's why this stuff we're doing is so powerful. It allows you to arrive at non-obvious results. Last but not least, let's talk about the half angle identities, and I'll just state them. So like, what is the cosine of alpha divided by 2? Well, maybe I should make you for extra credit on how you get this. 1 plus cosine alpha. This is true. And you can find it using first principles. Okay. And let's give you one of the tangents, but there's a lot of tangents. Okay. So you could use these guys. So for instance, to find what is the cosine of 15 degrees? Well, notice that if alpha over 2 is equal to 15 degrees, that implies that alpha is equal to 30 degrees. So that in this equation, this implies that the cosine of 15 degrees is the same thing as plus or minus the square root of 1 plus cosine of 30 degrees. Everything divided by 2. And we know what the cosine of 30 degrees is. So we can find out what the cosine of 15 degrees is. Because cosine of 15 is not a special angle. But we can use the special angle cosine of 30 degrees to discover what this non-special angle expression is. Cosine of 30 degrees is root 3 over 2. So you can just replace this with root 3 over 2 in your expression. This plus or minus here dictates which quadrant are you in. So for 15 degrees, we're in quadrant 1, and cosine assumes positive values, so we will forget the negative. And so, what is the cosine of 15? Well, it's that. But what is that? Well, it's this. Okay, but what is that? Well, multiplying top and bottom by reciprocals, it's this. Oh, wait. So I actually messed up here. This needs to be over 4. That's what the cosine of 15 is. So we weren't wasting our time coming up with different expressions like that. Notice that it allows us to easily discover new values utilizing our old special angle values. Okay. Take 5.